Welcome to the deep dive. Today we are actually pulling directly from prep materials for the TEAS and HESI A2 nursing entrance exams.
Yeah, we're diving into the mathematics of constraint.
Exactly. Our mission today is to really understand inequalities. Specifically what happens when things are, well, when they're not equal.
Right, which is a big shift for a lot of people.
It really is. I mean, think about it. School teaches us from day one to just absolutely obsess over the equal sign. We're trained to hunt down that one exact perfect answer.
You do the math, you isolate your variable, and boom, x equals 5.
Right. It feels incredibly precise, and honestly, it feels safe. But then, you step into the real world.
Yeah, you step into a hospital ward or like an engineering firm or a financial market.
And suddenly that equal sign is just nowhere to be found. The real world operates on safety margins, thresholds, minimums, maximums, all that stuff.
That's all boundaries.
Exactly. So today, for you listening, we're going to cover the surprisingly rich history of comparative math, the life or death rules of solving these bounds, and this is wild how a misunderstood mathematical constraint literally sank a 17th century warship.
Oh, that story is incredible. But to get there, we really need to understand that moving from an equation to an inequality requires a profound shift in how you view the world.
Oh, so?
Well, before you even try to solve one of these problems, you have to internalize that you are no longer looking for a single, solitary point.
Right.
You are exploring an entire region of possibilities.
Okay, let's unpack this.
Yeah.
If an equation is like having a reserved parking spot with your name painted on it, an inequality is like being told you have a permit to park anywhere in the entire south lot.
I love that.
Right? Like one is a specific point and the other is an entire region of valid options.
That analogy perfectly captures the structural difference. When you look at an equation, like say 2x plus 3 equals 7, that asserts two distinct expressions occupy the exact same value in space.
There's only one number in the universe that makes it true.
Exactly. But an inequality, like 2x plus 3 is greater than 7, asserts that one expression's value falls somewhere in this vast range relative to the other. The solution is a continuous interval.
What I find so wild in the source materials is how ancient this kind of comparative reasoning really is. I mean, we're talking about Babylonian and Egyptian problem texts.
Oh, yeah, they were doing this way back.
Right. They were reasoning about quantities being larger or smaller long before anyone had invented, dedicated symbols for it.
Which makes sense if you think about it.
It totally does. It's deeply intuitive to just look at two piles of grain and know, well, this one is bigger than that one, without needing any sort of algebraic notation.
Intuition definitely carries you through basic physical comparisons, but the formal symbolic apparatus took a surprisingly long time to catch up.
It really did.
Thomas Harriot, who was an English astronomer and mathematician, he's generally credited with introducing the distinct symbols for greater than and less than. And that was in an algebra text published in 1631.
Which was actually published 10 years after he died.
Right. Posthumously.
And considering he was an astronomer trying to map the massive scale of the cosmos, I mean, it makes total sense that he needed a formal way to define mathematical boundaries, rather than just exact points.
Absolutely. And the evolution didn't stop with simply drawing symbols on a page. The real leap happened when mathematicians realized inequalities were the key to unlocking higher-level theory.
Like calculus, right?
Yes, exactly. In the 19th century, Augustin Louis Cauchy used inequalities to formalize the entire foundation of calculus.
Because calculus is all about limits, figuring out how infinitely close you can get to a number without actually, touching it.
Precisely. A limit is fundamentally just a system of nested inequalities. Cauchy needed precise machinery to prove that as you squeeze a variable into a tighter and tighter boundary, the output gets trapped in a correspondingly tight boundary.
Wow.
And then, moving into the 20th century, this theoretical bounding just exploded into practical application. George Dantzig developed the simplex method for military logistics in 1947.
So we went from ancient farmers comparing piles of grain to astronomers mapping the stars, to mathematicians defining the infinite, to the military trying to optimize supply chains by satisfying massive systems of linear inequalities.
It's quite the trajectory.
It really is. That transition from point to region really sets the stage for everything a modern nurse or engineer does.
It does. And because an inequality represents an entire region of possible answers, solving one requires a slightly different toolkit than basic algebra.
Right, you can't just treat it exactly like an equal sign.
No, you can't. The physical mechanics look almost identical at first glance. I mean, you isolate the variable using inverse operations, But there is a fundamental underlying geometry you have to respect.
Let's talk about those boundaries, actually. We have strict bounds, which are simply greater than or less than. That implies you can get infinitely close to the boundary, but you cannot touch it.
Right.
Then we have inclusive bounds, greater than or equal to, and less than or equal to.
Yeah.
That means the boundary line itself is actually part of the safe region.
So keep those bounds in mind as we apply the mechanics. Suppose a nursing exam asks you to solve the inequality. Negative 3x plus 12 is greater than 0.
Okay, so the initial steps are identical to equation solving.
Yep. Walk me through it.
Okay, I want to isolate x. I'll subtract 12 from both sides, which leaves me with negative 3x is greater than negative 12.
Perfect.
Then normal algebra dictates I divide both sides by negative 3 to get x completely by itself.
And here's where you encounter the most heavily tested mechanic in the entire subject, the flip rule.
The dreaded flip rule.
Yeah, whenever you multiply or divide both sides of an inequality by a negative number, the inequality sign must flip direction.
So the greater than symbol becomes a less than symbol.
Exactly.
Okay, here's where it gets really interesting, but also a bit suspicious. Why should I believe the flip rule works?
What do you mean?
Well, when I learned this in school, it felt like a magic trick the teacher invented just to penalize me on tests. What is the actual mechanism happening there?
That's a great question. Think about the physical layout of a number line. Positive numbers grow larger as you move to the right, correct?
Right.
So 3 is mathematically greater than 2. Now multiply both of those numbers by negative 1. You get negative 3 and negative 2.
And on the negative side of the number line, negative 3 is further to the left. It's colder, it's deeper. So negative 3 is actually less than negative 2.
Exactly. The act of multiplying by a negative number physically mirrors the entire universe across the 0 point. Everything that was pointing to the right is now pointing to the left. Yeah, the magnitude stays the same, but the relative direction is completely inverted. The flip rule isn't a magic trick at all. It is literally an accounting mechanism for the fact that you just turn the number line upside down.
Let's actually test that to prove it. If I do the math on our problem, negative 3x divided by negative 3 is x. Negative 12 divided by negative 3 is a positive 4.
Right.
I flip the sign, and my answer is x is less than 4. Now, if I plug in a number less than 4, say 0, back into the original problem, negative 3 times 0 is 0.
Yep.
Plus 12 is 12, and 12 is indeed greater than 0. The math holds.
Now, consider the real-world consequences of treating that problem like an equation and ignoring that number line reflection.
It would be bad.
If you forgot the rule, you would have answered x is greater than 4. In a clinical setting, you just inverted a safety constraint.
You go from ensure the patient receives less than 4 milligrams to ensure the patient receives more than 4 milligrams.
Exactly.
That is a terrifying, potentially lethal mistake.
Which is exactly why entrance exams weight this specific rule so heavily. It is a rehearsal for recognizing that negative coefficients change the fundamental orientation of your limits.
This continuous math runs into a brick wall when you deal with physical objects, though, doesn't it? Variables in reality aren't just abstract points floating on an infinite line. They are constrained by context.
Absolutely.
The source materials present this scenario where a nurse practitioner determines a patient can receive no more than 3,200 milligrams of a medication per day, right? And the medication only comes in 400 milligram tablets.
Setting up the inequality. If it is the number of tablets, our constraint is 400 times it is less than or equal to 3,200.
Right.
You divide both sides by 400, a positive number, so no sign flip is required, and you arrive at is less than or equal to 8.
The continuous math tells me the solution set is anything less than or equal to 8. But, like, I can't hand a patient 6.5 tablets or 7.2 tablets.
No, you can't. The physical context of the problem restricts your real-world answer to whole, discrete integers. 0, 1, 2, 3, all the way up to 8.
So no fractions allowed.
Right. Exam writers love to exploit this tension between continuous algebraic solutions and discrete physical reality. You always have to reevaluate your mathematical answer against the actual physical constraints of the word problem.
That makes total sense. Let's pull back a bit and look at what happens when you have boundaries on both sides. You know, a floor and a ceiling.
Compound inequalities.
Yeah, the classic medical example is resting heart rate, where a normal adult range is between 60 and 100 beats per minute.
Written out, that is, 60 is less than or equal to h, which is less than or equal to 100. You are stating that the heart rate is greater than or equal to 60 and simultaneously less than or equal to 100.
And sometimes these exams will just stick an entire algebraic expression into that middle section, right? Something like 60 is less than or equal to 2h plus 10, which is less than or equal to 100.
They do love to do that.
If I want to isolate h, I have to respect all three zones of the problem at the same time.
Exactly. The fundamental rule of algebra, what you do to one side, you must do to the other, expands into this three-part harmony. You must subtract 10 from the left boundary, the middle expression, and the right boundary, all at once.
So subtracting 10 everywhere drops the bounds to 50 is less than or equal to 2h, which is less than or equal to 90. Yep. Then I divide all three parts by 2, leaving me with 25 is less than or equal to h, which is less than or equal to 45.
You got it.
So what does this all mean for someone gearing up to work in allied health? Bounding a value between a floor and a ceiling like checking if blood glucose or oxygen saturation is within a safe range, that is the primary cognitive task required at the bedside every single hour of a shift.
You are constantly determining whether a physiological value is safely inside that bounded segment. Visualizing these limits is a crucial skill, really, because human beings process boundaries much better visually than they do abstractly.
Let's walk through how we actually graph these out then. For a one-variable inequality, we are just working on a single number line. You plot a circle at the boundary value.
And the type of circle you draw carries all the mathematical weight. If your inequality is stripped less than or greater than, you leave the circle open and unfilled.
Meaning the boundary itself is off limits.
Correct. But if your inequality is inclusive, less than or equal to, you draw a closed, solid circle.
This boundary detail is critical. You know, a patient's core temperature must be less than 101 degrees gets an open circle. But a patient's temperature must be at or below 101 degrees gets a closed circle.
Exactly.
If the thermometer reads exactly 101.0, that is a fail in the first scenario and a pass in the second. The visual representation just completely prevents ambiguity.
And when you graph a compound inequality, like that normal heart rate range of 60 to 100, you plot two closed circles and just shade the space between them. You are visualizing a bounded finite segment of safety, rather than some endless arrow pointing to infinity.
But what happens when we introduce a second variable, moving from a 1D number line to a 2D coordinate plane? Say we have an x and a y.
The logic scales up perfectly, actually. Take y is greater than 2x plus 1. You first graph the boundary as if it were a simple linear equation, y equals 2x plus 1.
Okay, that's easy enough.
But instead of open and closed circles, you use the line itself. A strict inequality requires a dashed line. Think of it like an electric fence you cannot touch. An inclusive inequality gets a solid line.
Then you have to shade an entire half of the coordinate plane to show where the infinite number of correct x-y combinations live.
Yes, you do.
Now, I've heard people use a shortcut here. If it says greater than, just shade above the line. But given how these equations can be structured, that feels risky.
It is extremely risky. That shortcut only works if the inequality is perfectly solved for y on the left side. If the exam gives you x is greater than 2y plus 1, and you blindly shade above because you saw a greater than sign, you will likely shade the completely wrong half of the graph. Yeah, the relationship between the variables dictates the geometry, not just the direction of the symbol.
So instead of a shortcut, I want a foolproof method. What if I pick a test point, like a coordinate, that is clearly not touching the boundary line? Maybe the origin. It's 0, 0, and I plug x equals 0 and y equals 0 into the inequality.
That is the way to do it.
Yeah.
You will immediately see if the statement is true or false. If plugging in the origin yields a true statement, you shade the side of the line containing the origin.
And if it's false?
If it yields a false statement, you shade the opposite side. The test point method relies on the actual mechanics of the constraint, not some memorized visual trick.
Speaking of the physical reality of constraints, this brings us to one of the most incredible historical case studies in the source material. The Swedish warship Vasa in 1628.
Such a wild story.
We were talking about an engineering disaster where an inequality was violated in real time.
The Vasa was designed to be the most heavily armed ship in the Baltic. But on its maiden voyage, it sailed roughly 1,300 meters from the harbor, caught a mild gust of wind, capsized, and sank right in front of a massive crowd.
It's crazy. We tend to think of stability as a static, exact number. But naval architecture actually relies on a dynamic system of inequalities.
Right. The physics of a sailing ship involve two competing rotational forces. The wind hitting the sails creates the heeling moment, the force actively trying to tip the ship over.
Okay.
Counteracting that is the righting moment, the force generated by the ship's center of gravity and hull buoyancy, which is actively trying to pull it back upright.
So the fundamental inequality of naval architecture is that the righting moment must be strictly greater than the heeling moment at all times, across a whole range of tilt angles.
Exactly. But the King of Sweden demanded a second deck of heavy bronze cannons be added late in the construction process.
That sounds like a bad idea.
It was. This massive amount of weight high up on the ship drastically raised the center of gravity, which severely weakened the righting moment.
They shrank their own safety margin.
Drastically. So when that mild gust of wind hit the sails, the heeling moment suddenly spiked. Because the righting moment was so weak, the heeling moment became strictly greater than the righting moment.
Oh, no.
The physical constraint was violated, water poured in through the lower gun ports, and the ship went down. Physics enforced the inequality without mercy.
The Vasa sank because of physics, but in modern times, ignoring the underlying mechanics of inequalities can sink our finances or, completely corrupt our data. Our sources highlight some fascinating mathematical traps here, starting with the arithmetic mean geometric mean inequality, or AMGM.
The AMGM inequality is a fundamental theorem. It states that for any set of non-negative numbers, the arithmetic mean will always be greater than or equal to the geometric mean.
So most of us know the arithmetic mean. You add up the numbers and divide by how many there are. But how does this mathematical truth turn into a financial trap?
Imagine you invest your life savings in a mutual fund. In year 1, the market crashes, and the fund drops by 50%. In year 2, it rebounds and gains 50%.
Okay, I'm following.
A fund manager can calculate the arithmetic mean. A 50% loss plus a 50% gain equals 0. Divided by 2 years is 0. So they market the fund as having a 0% average annual return.
That sounds like I broke even. But let's actually trace the money. If I start with $100 and I lose 50%, I am down to $50.
Right.
In year 2, I gain 50% on that remaining $50. Half of 50 is 25. So I end year 2 with $75. I didn't break even at all. I've actually lost 25% of my entire investment.
Exactly. The arithmetic mean systematically hides volatility. To find out what actually happened to your money, you need the geometric mean, which calculates true compounded growth.
How does that work?
Instead of adding, you multiply the growth factors. A 50% loss is a factor of 0.5. A 50% gain is a factor of 1.5. You multiply 0.5 by 1.5 to get 0.75, and then take the square root.
And the square root of 0.75 is roughly 0.866.
Which translates to an actual compounded annual loss of about 13.4% per year. The AMGM inequality basically guarantees that the arithmetic mean will always paint a rosier, mathematically greater picture than the geometric mean.
Wow.
Financial marketers exploit this inequality to sell you on growth that doesn't actually exist.
It is incredibly sneaky because it is technically a true mathematical statement, just applied to the wrong mechanism.
Yeah.
And we see a similar misuse of boundaries in statistics, particularly with Chebyshev's inequality from 1867.
Pafnuty Chebyshev formulated an incredibly powerful inequality. It guarantees that no matter what your data looks like, at least 75% of it will lie within 2 standard deviations of the mean.
So it's completely distribution-free.
Yes. It requires 0 assumptions about the shape of your data.
But the source material contrasts this with the empirical rule, which states that about 95% of your data lies within 2 standard deviations. 95% is a much tighter, more precise boundary than 75%.
It is. But the catch is that the empirical rule only works if your data is perfectly normally distributed, like a flawless bell curve. If your data is skewed or has fat tails, the 95% rule collapses entirely.
So analysts are faced with a choice between being mathematically safe but vague with Chebyshev, or highly precise but incredibly risky with the empirical rule.
Precisely.
If someone uses the empirical rule on weird, non-normal data, they're essentially hallucinating a tight boundary that just does not exist in reality.
It is one of the most common statistical misuses. People crave the precision of a 95% bound, so they simply assume their data fits the required bell curve. They violate the constraint of the rule to get an answer that sounds better in a boardroom presentation.
We have covered a massive amount of ground today, pulling from deep theoretical math to actual clinical and historical applications. Let's recap the critical takeaways for you, especially if you're taking the TEAS or HESIs soon.
First, master the flip rule. If you multiply or divide an inequality by a negative number, you must flip the sign. Remember that you are effectively turning the number line upside down.
Right.
Second, pay close attention to your graphing mechanics. Strict bounds require open circles and dashed lines. Inclusive bounds require closed circles and solid lines.
Third, when handling compound inequalities with a floor and a ceiling, treat them as a three-part harmony. Whatever operation you apply to the middle variable, you must apply to both outside boundaries simultaneously.
Fourth, never lose sight of the fact that your solution is a range, not a single point. Verify your algebra by testing a point inside your proposed safe zone and another point outside of it.
Love that.
And finally, use the origin as a test point for two-variable shading rather than relying on structural shortcuts.
The overarching theme here is that inequalities are the invisible architecture of constraint. When you look closely, you really see them governing everything. Minimum wage laws, highway speed limits, credit score approvals, the structural integrity bridges, and the exact drip rate of an IV bag.
They're everywhere.
These are all mathematical inequalities dictating the acceptable boundaries of human activity.
They provide the vocabulary we use to measure safety, calculate structural tolerance, and quantify the physical realities of the world.
Which brings us to a final thought for you to mull over today, building on the tension we saw with Chebyshev in measuring uncertainty. We live in a society that is practically addicted to the exact answer.
Oh, definitely.
We desperately want the equal sign. We want to know exactly what to do, exactly how much money a fund will return, and exactly what the future holds. But as the transition from basic algebra to advanced probability shows us, maybe true mathematical maturity, and perhaps even life wisdom, isn't about finding that perfect solitary point.
That's a great point.
Life rarely happens at an exact coordinate. It happens in a region. Wisdom isn't about eliminating all variables to find one perfect answer. It's about becoming perfectly comfortable defining the boundaries of your own uncertainty. It's about knowing exactly where the safe region begins and ends, and realizing that sometimes the equal sign was just an illusion all along.